Let us now do a few problems. A 480 volt 60 Hz 50 HP 3-phase induction motor is drawing 60 amperes at 0.85 power factor lagging. The stator copper losses are 2 kilowatt and the rotor copper losses are 700 watts. The friction and windage losses are 600 watts. The core losses are 1800 watts and the stray losses are negligible. Find air gap power, power converted, output power and the efficiency of motor. Okay. So a few of the losses are given and we have to find some powers. First we will write down what are all the losses that are already given. So we have the stator copper losses. This is 2 kilowatt. And the rotor copper losses is given as 700 watt or 0.7 kilowatt. Right? Then friction plus windage losses is given as 600 watts. Finally, core losses. This is given as 1800 watts or 1.8 kilowatt. This also you can write in kilowatt. Also, in addition, the stray losses you can take as 0 because it is given as negligible. Next, what else is given? You have here, this is the rated conditions. Okay, 480 volts, 60 Hz and 50 HP. And this motor is drawing 60 amperes at 0.85 power factor lagging. Okay, so that means we can get the input power here because the current being drawn is given. So first you can anyways write down the given information. V rated is 480 volt and the P rated is 50 HP. And what is the current that is being drawn? This is given by 60 ampere. So you can take it as I1 and the power factor is given as 0.85 lagging. So from here we can find out the input power as root 3 V rated into I1 cos phi. Okay. So what is this? Root 3 into 480 into 60 into 0.85. Why we are taking V rated here? Because as long as nothing is given about the voltage, we assume that the motor is running at the rated voltage. So this, if you calculate, you are going to get 42.4 kilowatts. Okay. Now we can find out the air gap power. Okay. So this is the first bit that we are trying to find out. Air gap power PG is equal to the input, the power input minus the stator copper losses. Stator copper losses minus what else will come here? The core losses as well. Because remember, rotor core losses we are ignoring, only the stator core losses. So this is equal to 42.4 minus 2 kilowatt minus 1.8 kilowatt, which you are going to get 38.6 kilowatt. Okay. So this is the air gap power. What is the next thing that you have to find? The converted power. So the converted power you will get when you subtract the rotor copper losses from the air gap power. Okay. So this is a very simple problem. We are just following the power flow diagram. P converted is equal to PG minus P rotor copper losses. So this is equal to 38.6 minus rotor copper losses is given as 0.7. So you're going to get 37.9 kilowatt. Next, what do you have? You have to find out the output power. When you're giving the rated voltage, you will get the rated output. So that means the output power will be 50 horsepower. Okay, but we can find from the power flow diagram as well and we can see if it is right or not. Okay. So P output is equal to, from the converted power, you have to subtract the friction and windage losses as well as the stray losses. They are collectively called rotational losses, right? Since there are no stray losses, you're only going to have friction plus windage losses. So this is given by 37.9 minus 0.6. So you're going to get 37.3 kilowatts. If you want to convert into HP, what is the conversion factor? 1 HP is equal to 746 watts or 0.746 kilowatt. Okay. So what will be 37.3 kilowatt? It will be 37.3 divided by 0.746. Okay, HP. Thus you are going to approximately get 50 HP, that which is already given. Okay. Next, what else is given? We have to find the efficiency of the motor. So finally, efficiency. What is efficiency? Output by input power. So output we have seen anyways, it is 37.3 kilowatt. And what is the input power that we calculated? We got it to be 42.4 kilowatt. Okay. So 42.4 kilowatt. So this, if you calculate, you're going to get 87.9 percentage. Okay. Remember to make sure that these units are same. Don't take the horsepower here and kilowatt here. Okay. Next question we have a 460 volts 25 HP 60 Hz 4 pole Y connected induction motor has the following impedances in ohms per phase referred to the stator circuit. So R1, X1, R2 dash, X2 dash and Xm are given. The total rotational losses are 1100 watts. The core loss is lumped in with the rotational losses. For a rotor slip of 2.2% at rated voltage and rated frequency, find speed, stator current, power factor, P converted and P output, T induced and T load. So we will see how to do this. First we will write down whatever information is given. Okay. The rated voltage is given as 460 volts. P rated is given as 25 HP. Remember that rated power is usually the output power that the motor is able to deliver. Next, number of poles is given as 4 and the parameters we can represent in the circuit. Since RC is not given, we can assume it to be negligible. This part of the circuit is given. Okay. So what is R1? This is given as 0.641. JX1 is given as J 1.106 ohms. JXM is given as J 26.3. R2 dash is given as 0.332. But you have to remember the actual value of the resistance here is R2 dash by S. Okay, so we are only writing down the R2 dash value here. And X2 dash is given as J 0.464 ohms. Okay. Next, rotational losses, total rotational losses is given. It is also given that core loss is lumped in with the rotational loss. So what we can do is the rotational loss plus the core loss together we can take it as a constant loss, which is 1100 watts or 1.1 kilowatt. Okay. Next, what else is given? The slip is also given. The rotor slip is given in percentage. S is equal to 2.2 in percentage or 0.022. Now, what is the first parameter that you need to find? It is the speed. So first we will find the synchronous speed. Ns is given by 120 F by P. Okay. So the frequency is also given here. What is the frequency? It is given as 60 Hertz. So this also you can write here. F is equal to 60 Hertz. So this you are going to get 1800 RPM. Okay. Now what is the actual speed? This is equal to 1 minus S times Ns. S. So 1 minus 0.022 into 1800. So this you are going to get 1760.4 RPM. Okay. Now what is the next question? We have to find out the stator current. So the stator current will flow like this. And what about the voltage that is appearing here? See, the rated voltage is given as 460 volt. But the equivalent circuit that we draw, this is per phase. Now usually the rated voltage will be the line to line voltage. So this is going to be 460 divided by root 3. This will give you the per phase voltage. Now another thing that you can see here is the rotor conductors, it will be short circuited here, right? Because in the machine we are shorting out the rotor conductor bars or the conductors that we have. Okay. So what we have to do to find I1, the stator current, we just need to divide the 460 by the equivalent impedance. So we will find out the equivalent impedance. Z equivalent is equal to 0.641 plus J 1.106. This entire thing is in series with JXM, which is J26.3. This is in parallel to the series combination of R2 dash by S. Okay, remember this resistance value is not R2 dash but R2 dash by S. So you will write here 0.332 divided by the slip. Slip is given as 0.022. So this is in series with JX2 dash, which is J.464. So this equivalent impedance you are going to get 11.72 plus J7.79, the rectangular coordinates form, or in the magnitude phase form if you want, 14.07 angle 33.6 degrees. Okay. So this will be in ohms. Now we can find out the stator current. This is equal to 460 divided by root 3 divided by the equivalent impedance 14.07 angle 33.6 degrees. What about the phase here? We take it as 0 degrees. The voltage is usually taken as the reference phasor. So this if you calculate, you are going to get 18.875 angle minus 33.6 degrees amperes. Next, what is the next question that we have? We need to find out the power factor. So in the stator current, if you can see, the current is lagging behind the voltage phasor. Voltage is at 0 degrees and the current is at minus 33.6 degrees. So this is the power factor. Cos of this angle will give you the power factor, right? So we have power factor is equal to cos 33.6 degrees, which you are going to get 0.833. Now is this leading or lagging? It is lagging power factor because the current is lagging. Next question. In the next question we have P converted and P output we have to find out. Now how do we find out? First the converted power. P converted, this is equal to, we can write in terms of the air gap power as 1 minus S into Pg. Now S we know, we need to find out Pg. What is Pg? The air gap power. This is equal to the input power minus the stator copper losses. Okay. So the input power, how we can find? We know the input voltage, input current and power factor. So we can find out input power root 3 into VLIL cos phi. Remember the line voltage. If you are taking phase voltage, then you have to write 3 here. 3 V phase I phase cos phi. So we will take the line voltages minus, this is the input power, minus what is the stator copper losses? It will be 3 times I phase square into the stator resistance, which is R1. Okay. So now we know all of the values here. What are all the values? The line voltage is 460. The stator line current or the phase current, it is one and the same in the Y connection. So here you are going to get 18.875 into what is cos phi? 0.833 minus 3 times 18.875 square into 0.64. This if you calculate, you are going to get 11.843 kilowatts. Okay. So now we can find out the converted power. 1 minus 0.022, which is the slip, into 11.843 kilowatts. So this you are going to get 11.582 kilowatts. Okay. So this is the converted power. Now what about the output power? P output you can get from the, if you subtract from the converted power, if you subtract the rotational losses, then you are going to get the output power. So the rotational losses is given already in the question, 1.1 kilowatt. Okay. Remember the units, you have to be very careful. You are taking kilowatts here. So 1100 watts you have to convert into kilowatt. These are some silly mistakes that you often do. So you are going to get 10.482 kilowatt. And the last question we have T induced, the induced torque and the load torque or the output torque we have to find. So what will be the induced torque expression? The converted power divided by the angular speed. Okay, remember, not in RPM but the angular speed omega. So this is going to be converted power, we have seen it is 11.582 in kilowatts. Okay, so we will write 11,582 divided by omega m, we need in radian per second. So this is omega m is equal to 2 pi into Nm by 60. Nm is in revolution per minute, omega m is in radian per second. So this is we got as 1760.4 divided by 60. So this we are going to get 62.82. What is the units? It is Newton meter. What about the load? This is the actual output power that is available divided by the speed. So the actual output power we have seen it is 10.482. This is equal to, okay. So 10,482 divided by 2 pi into 1760.4 divided by 60. So this you are going to get 56.85 Newton meter. Next we have a past year gate question. For an induction motor operating at a slip S, the ratio of the gross power output to air gap power is equal to what? So we need it in terms of the slip. So this question is actually pretty simple, provided that you know what is exactly gross power output. Is it the P output or the P converted? Okay. So the gross power output we call the converted power as the gross power output. Okay. So now we want the ratio. Once this is known, then it is very simple. We want the ratio P converted by Pg. We know P converted is 1 minus S times Pg divided by Pg. You are going to get answer B. So here you have a conceptual question, past year gate question. Leakage flux in an induction motor is, okay. So flux, option A is flux that leaks through the machine, flux that links both stator and rotor windings, flux that links none of the windings, and finally flux that links the stator winding or the rotor winding but not both. So for this we need to understand what kind of flux we call as the leakage flux. Okay. So when there are two windings, basically the induction machine or to that matter a transformer, how do they work? One winding will have current through it, and the flux that is produced, this should link the second winding. If it is not linking the second winding, that means if there is a flux which is say passing like this, then this is not useful flux. This is not being useful to us. Okay. So this is what we call as the leakage flux. Leakage flux. And this is the useful flux. So by definition, leakage flux is something that doesn't link one of the windings. Okay. So we have option D. It is the flux that links the stator winding or the rotor winding but not both.